So last time we introduced the RG transformation, and we derived the relation between this untransformed and rescaled coupling constants, and they have such matrix relations delta Kn prime, where Kn refers to the collections or set of your coupling constants. So, for example, in the Ising model, in the presence of the magnetic field, this Kn is actually the two-dimensional parameters, K and H, that we introduced earlier. You can imagine that Hamiltonian near this fixed point, Kn star, under Rg, this coupling constant will not change. So all the critical properties are determined near that fixed points. So we could analyze these Rg transformations near this Kn star fixed point, and we imagine that this Hamiltonian near that fixed point is given by this fixed point Hamiltonian plus some deviations. And these deviations are given by the deviations of the coupling constant from the fixed point value. And we could perform this Rg scaling or Rg transformations near that fixed point so that Kn becomes Kn prime, and the Kn prime is the transformed coupling constant set. But we know that this delta Kn prime should be very close to delta Kn. They differ only by some kind of a linear equations from this Taylor expansion. Okay, so you could Taylor expand this delta Kn prime in terms of the linear equations, made of this matrix product between the matrix M, which consists of the first derivative of the coupling constant in the prime system with respect to the unprimed coupling constant. For example, in the Ising model, under field, this matrix M is written in terms of the 2x2 matrix. So there are 4 elements, and they are partial K prime, partial K, and partial K prime, partial H, and partial H prime, partial K, and also partial H prime, partial H. Of course, not all of them are non-zero, but in general, they could be represented in terms of a 2x2 matrix, and therefore this delta Kn prime is nothing but this kind of a linear combinations of this different derivative component multiplied by this delta Kn, which is the untransformed deviation of the coupling constant. In other words, delta Kn prime is contributed from different set of a direction of this coupling constant. For example, you have the contribution of delta K prime, for example, in the Ising model, from this partial K prime, partial K, but also it could actually come from this partial H prime, partial K. Okay, likewise, the delta H prime could be contributed from the original K direction, also the original H direction. So each coupling constant under Rg transformations acquire contributions from all of the coupling constants changes. Okay, so it's a linear superposition of little difference along all these directions of the coupling constant vector. Therefore, we could use the matrix product to rewrite this delta Kn prime in terms of such a kind of a linear superposition of all different tiny little bit coupling constant changes along all the directions. So as I mentioned last time, that the matrix M is very important in this Rg analysis because it gives us eigenvalues and also eigenvectors. And as we'll see later, that eigenvalues lead to the critical exponents that we proposed previously. Remember y, h, and yt. And the eigenvector leads to the scaling fields where all these power law scaling behaviors are based. Okay, and very importantly, this matrix M forms so-called semi-group, because if you successfully perform this Rg transformation twice, first by B2 scaling and then by B1, and the resulting transformation could be represented by a single scaling, where the scale factor is nothing but B1 times B2. So such property is called a semi-group property, and if we represent this eigenvector by this little e vector with a sigma superscript representing the direction of this eigenvector, and this lambda represents the eigenvalue with the subscript, and then we could rewrite this semi-group property in terms of this eigenvalue properties, right? So this matrix M acting on this eigenvector gives you this eigenvalue times this eigenvector. So that's the eigenvalue equation. So if I use this eigenvalue equation, plug in this semi-group properties, and I can immediately get this eigenvalue relations between 2 steps RG and 1 step RG. Okay, so you immediately see that if this lambda B1 times lambda B2 is actually the same as lambda but B1 times B2, so you immediately solve this equation. This is only solutions, which is the power law in B, because you immediately see that B to the power of y sigma satisfy this relation. So B1 y sigma, B2 y sigma is actually B1 times B2 altogether y sigma. And this is also the confirmation of our earlier assumption that this scaling behavior is the power law, in that scaling ansatz or scaling hypothesis. Remember that either Witten's proposal or the Katanov's proposal, so they all assume that this is the power law behavior. So this y sigma is a so-called critical exponents, which is independent of this scale factor B, and this y sigma comes from this eigenvalue, the power law exponent of the eigenvalue, and we will see that in just a moment. So now let's look at the so-called RG flow, but we first ask these questions: how does this delta k vector transform under this RG transformation? We know this delta k. How about we perform this RG scaling? So the delta k is transformed into delta k prime. And how do we represent delta k prime in terms of this matrix M? So as we notice and defined over there, that delta k is actually vector. So which represents the, for example, this is delta k and delta h. For the IC model under field, the vector which describes the deviation of this coupling constant from the fixed point value along all these directions of this coupling constant. So it is in general a vector, and this vector could be decomposed in terms of the eigenvector or eigendirection. As we can see over there, that the eigendirections are all orthogonal and normalized, and therefore you can consider this as our new unit vector in length scale. Okay? So that any vector could be expressed in terms of a linear superposition of this unit vector. Right? So this E hat sigma is actually our new unit vector. So you could imagine that this any vector delta k could be decomposed in terms of these linear combinations of this unit vector, but this delta k vector will get changed under RG. So how does it change? Well, it changes according to this M matrix multiplied by this delta k vector. Remember that. And therefore, you could just plug in the definition of delta k vector, and as a linear superposition of these all eigendirections. And we know immediately that if you add this matrix M onto the eigenvector, based on this eigenvalue equation, you get this eigenvalue lambda sigma multiplied this eigenvector itself. As a result, you can see that under RG, this coefficient, which we call this projection of this delta k prime in the direction of this E eigenvector direction. So this projection gets modified. Before this RG is performed, this projection, which is a coefficient in front of this linear combination of the eigendirection, is called A sigma. But now it is A sigma times lambda sigma. And we know that lambda is actually b to some power y sigma, which can be either greater than 1 or smaller than 1 or equal to 1, depending on whether y sigma is actually positive or negative or 0. So in other words, under RG, this coefficient, which is a projection of your delta k along some eigendirection, could be either increased or decreased or the same, depending on this exponents y sigma, which is the critical exponents. Okay, that is precisely the meaning of the relevant, irrelevant, or marginal variables. Okay, so therefore we could actually categorize the RG transformation in terms of the three classes. And the first class is when y sigma is positive, then you know that the eigenvalue is actually larger than 1. As a result, when you perform the additional RG transformations, this projection gets progressively enlarged. It gets increased. So we call this the components or the projections of this delta k along that direction, will grow under RG. And this is how we call this variable the relevant variable, okay, because the coupling constant changes actually increasingly larger, okay, which means that this coupling constant becomes more and more important under RG. And the second case is that when y sigma is negative, which means that this eigenvalue lambda is actually less than 1, in that case, this coefficient shrinks, gets decreased under RG. So you could imagine that if I decrease this coefficient by a factor of, say, 0.9, and after the second iteration under RG, and this decreasing factor becomes what? 0.9 squared, right? Which is 0.81. So under RG iterations, and this coefficient gets progressively smaller and smaller and smaller, and after infinite number of iterations, and this coefficient vanishes. And what does it mean that this coefficient vanishes? Well, this means that this delta k, or this coupling constant itself, vanishes along that direction. And so in that case, we call this variable is irrelevant variable, because it is irrelevant, okay, because that coupling constant flow to 0, and we could disregard that coupling constant near the fixed point. Of course, all the coupling constant play a role here, but near the fixed point, we only care about the leading relevant variables, which is the first case, this y sigma is a positive value. And the third case is when y sigma vanishes. In that case, this lambda eigenvalue is actually 1, which means that you don't change anything after RG iterations, which means that your coefficients become exactly the same before and after the transformation, and therefore the coupling constant don't change in magnitude. And in that case, we call this variable is a marginal variable. Marginal meaning is at the border of relevant and irrelevant. It is marginal. So of course, this is just simple RG analysis based on this power law behavior, but more sophisticated calculations can be done, and we could further classify these marginal variables into marginally irrelevant, marginally relevant, and marginally marginal variables, depending on these higher order contributions to the RG equations, and we may see that later. So that's the significance of this RG transformations in terms of this relevant or irrelevant or marginal nature of the variables. And after many iterations, of course, it is the relevant operator or relevant parameters or couplings that will survive, and all these irrelevant couplings could be thrown away, and the marginal could also be stored away compared to this power law growth of this relevant variables. Okay, so let's take a short break. When we come back, we will continue describing the topology of this RG float under RG transformations. So let's discuss the topology or the RG flow phase diagram in terms of the parameter space and under RG transformations, and we will see how this coupling constant will flow under RG. So this is the typical phase diagram for the Ising model with nearest neighbor spin interactions and the next neighbor spin interactions of Ising type and in the presence of external magnetic field. So it is a slightly more generalized version of our earlier version of the Ising model on the field, where we only discussed the nearest neighbor version of the Ising coupling. But this two-dimensional RG flow shall reach much richer information than the this nearest neighbor Ising model. So this is the two-dimensional phase diagram in terms of the K1, which is J1 divided by KBT, and K2, which is J2 divided by KBT, where J1 and J2 refers to the Ising coupling of the nearest neighbor and next nearest neighbor. So there are two important curves in the phase diagram, which is marked by yellow and by red, and they cross at this critical fixed point right here, and there are many arrows indicating direction of the RG flow. So there are several fixed points here. One is the critical fixed point, which separates this high temperature phase or high temperature fixed point at 0, 0, because in the high temperature limit, when temperature goes to infinity and this K1 and K2 both vanish. Okay, so this represents the high temperature phase of the model, which is given by this fixed point value 0, 0 of K1 and K2. And there is a low temperature fixed point where this K1 and K2 become infinity. Okay, so these two different fixed points characterizing two different stable phases. So we will talk about this stable and unstable in just a moment. And along this x and y axis, there are one fixed point per axis representing this nearest neighbor Ising fixed point and next nearest neighbor Ising fixed point. So suppose the nearest neighbor fixed point is the fixed point where there's no K2, no next nearest neighbor couplings. And likewise, this fixed point in the y-axis is the fixed point of the next nearest neighbor Ising model with no nearest neighbor coupling. Okay, so we know very well that these two fixed points exist individually. If we just talk about this nearest neighbor only Ising or next nearest neighbor only Ising, but in general, if both couplings are present, then there is a special critical fixed point right in the middle. So let's talk about these arrows. Represents the direction of the RG flow. And each point in this phase diagram represents a set of a coupling constant combination. And you could start at any given point in this phase diagram and start doing these RG transformations. And the arrows will tell you how this coupling constant will flow. So for example, if I start from here, just slightly below this critical fixed point right here, and which means that this J1 is actually below that critical value in the x-axis, and J2 is actually below that value over here. So I'm in the high temperature side of this phase diagram. So if I start from here as an initial coupling and I start doing the RG transformation, and after this one iterations, I will follow the direction and the red curve. Okay, so I come here, and then this both couplings get smaller and smaller and smaller as you keep iterating this RG transformations. And after infinite number of iterations, and my initial coupling will flow to this 0, 0 fixed point, which is the high temperature fixed point. Okay, so likewise, if I start from here as a starting point, and eventually I will flow to infinity, infinity, which is a low temperature fixed point. So to determine the shape of this kind of a critical manifold, we should study this eigenvectors of this M matrix that I just introduced to you. Okay, but suppose I know these solutions and I can easily interpret this RG flow diagram in terms of this unstable directions and stable directions. So likewise, if I start from here, then or here, I will just flow to this critical point. If I start from here, then I could just flow there. So likewise, for the other flows near these other fixed points are the same. Okay. So if I'm not along this critical manifold marked by red and yellow, if I'm here, then I could simply just follow this curve all the way to 0, 0. If I'm here, I could follow this curved RG flow back to 0, 0, and so on and so forth. So I can be anywhere in the phase diagram, and I start from there, and I do this RG transformation and end up with only 1, 2, 3, 4, 5 possible places, 5 fixed points. Here, there, 3, 4, 5. Okay, no more solutions and no more places to hide. Okay, so I can only be one of these 5 fixed points after infinite number of iterations. And this fixed points is actually characterizing these phases. For example, this 0, 0 is the high temperature phase, and this infinity, infinity is actually low temperature phase, and these two are this nearest neighbor, next nearest neighbor Ising critical point. But this special point in the middle is actually the critical fixed point. It describes neither this 0, 0 high temperature phase nor this low temperature phase, but it is the critical point separating these two stable phases. Okay, so the definition of this critical point is that it at least has these two unstable directions, and these two directions are flowing away from this critical point, which are marked by red curve. So you see that if I from either side of the red curve, and eventually, the couplings will flow away from that point. However, the yellow curve is actually the stable direction, where, if I come from either side of this critical point along the yellow curve, and it will merge to this stable fixed point. Okay, so the critical point must have at least 2 unstable directions. You can have all directions unstable, but you cannot have all stable directions for a critical fixed point. By definition, the critical point is a very fragile, unstable point. So that's the sort of interpretation of the RG flow diagram. So now let's look at the origin of the scaling by further perform some kind of calculations that we already did. So to simplify this calculation, we consider one relevant variable, which is suppose the nearest neighbor Ising model, and we know that it has the critical point at finite temperature called this TC1, and at a fixed nearest neighbor coupling J1, which we call J here. So under RG, this temperature gets transformed by this RB operator, which is kind of a matrix in general, but here is simply just some kind of operation, a linear operation. And T star is the fixed point temperature, or the critical temperature, where you don't change that value under RG. So we could linearize this RG relations by making this subtractions between T prime and T star, and which is given by this difference between these two transformations. And we could consider this is a very close temperature region to this T star, and so we could just Taylor expand this up to linear in T minus T star, and we ignore the higher order contributions to that linearized RG equations. And this lambda b is nothing but the eigenvalue that we just defined, which is in a single variable case, just a partial RB partial T, evaluated at T equals T star. And from the semi-group property, we know that this lambda b is actually the power law fashion, which is b to the power of yt, and T star is defined as Tc. So if we define little t, which is dimensionless temperature relative to the T star or Tc, and we could iterate this Rg n times, multiple times, and this little t becomes b to the power of yt to power of n times t after n iterations. So if I iterate this n times, and after the n iterations, this little t becomes t times b to the power of b to yt times power n. So to link this to the critical exponents, we consider this Rg transformation of the correlation length, which we have done some analysis earlier. So C prime represents transformed correlation length, which is C divided by B. Remember that. But we know that C of t after n iterations actually is equal to b to the power of n times C at that nth iterations. So following this one-step Rg, suppose we performed Rgm steps. Then this original correlation length as a function of little t becomes the renormalized correlation length multiplied by the factor b to the power of n. Okay, so now you can simply just plug in this Tn right here back to the argument of this transformed correlation length, and we can choose this b to the power of n, as I mentioned many times, that we could just play this trick as we like, because this factor of b is arbitrary, so we can actually choose whatever value for our convenience. And in this case, we just particularly choose this factor to actually cancel this dependence on t. So after this substitution, we immediately get that this correlation length as function of t before this Rg transformation is given by this formula, b inverse times t altogether power minus 1 over yt multiplied by C of b, which is simply just correlation length after one step Rg, which is finite. And this is given by definition t to the power minus nu. You know that this nu is actually 1 over yt by comparing this correlation length as a function of little t, and we know immediately that this nu is actually 1 over yt. And therefore, as long as we know yt, we know nu. So this is exactly the way that we obtained critical exponents, for example, this correlation length exponents. So we try to derive the Rg scaling equation. We try to solve those eigenvalues, eigenvectors, and the eigenvalue will become the critical exponents. So and this is the way that we analytically derive this correlation length exponent by Rg. And this is how the scaling arises after n iterations of Rg transformations. Okay, so in other words, the scaling phenomenon is nothing but the Rg transformation in the thermodynamic limit. After infinite number of iterations, you could reach this divergence or singularities or some kind of non-analytic properties of your system under infinite number of Rg transformations. And this is the way that we step by step derive such critical exponents. So that's enough for today. So we really like to solve this 2x2 matrix, the eigenvalues and eigenvectors, and determine this critical exponents and so on.